All right, everyone, welcome back. It's been a little bit of a minute, but that's okay. This project is far from forgotten. Um, we're picking up now in chapter 3 of Categories and Sheaves. We've sort of finally gotten through the first couple chapters, and now we're ready to start something, well, not unrelated, but new. These first couple chapters in the book all sort of represent some amount of background material that's leading us towards the ideas of homological algebra. And as part of that, we need to continue to sort of build some machinery. This chapter builds up ideas related to what are called filtrant limits and colimits. And some people call these filtered limits or colimits. And these are sort of generalizations of the p-adic numbers. And I know we had a distraction about those a while back. I'm readily distracted already enough, but probably at some point we'll return and maybe add some words to that discussion because I've since learned some more stuff since that video was made. So to get us off and running, I want to start by reminding myself and sort of pointing out to you guys that I make a hilarious, not an error, but a goof, which is that I call the tensor Hom adjunction such because I have a hard time remembering which one is the left and which one is the right adjoint. So I say tensor first because that way when I write it, tensor's on the left and Hom is on the right. However, I also do this annoying thing of calling the adjunction between the free and forgetful functors. I usually call that the forgetful free functor. I guess it sounds right in my brain because, like tensor Hom, I have the long word and the short word, and then the long word and the short word for forgetful free. But that's not right if my goal is to be consistent. What I should do is call it the free forgetful adjunction. So first off, I'm going to do that from now on as much as I humanly can. But this little hiccup in the way that I talk about functors is exactly relevant to where we're going. Because the point of this is to, of course, remember which adjoint is which in light of the idea that right adjoints preserve limits. And the question of which of the forgetful and free functors is which is relevant for the motivating discussion in Kashiwara and Shapira for filtrant limits. So the functor in consideration that we're going to want to look at is the forgetful functor. And we're going to look at the forgetful functor, which I'm going to call just f, because there's a lot of f's running around. And we're going to think of this as a functor from the category of modules over some nice ring. Like you could think about a abelian groups if you like, if you just want it to be Z. You could also think about a field if you want to do vector spaces. I'm going to write R mod for R, a not terrible ring, and leave to the commutative algebraists in the comment sections and in the Discord to figure out if it matters anywhere. I don't think it does, but I'm just not going to worry about it. So this will be a functor from R mod to set. And this commutes with projective limits, but not injective limits. And this is something that we have either said already explicitly or at least flirted with in the last chapter. I don't know if we've discussed this in particular, but this is one of those adjoints preserve limits business. So we know that which of the pair that it commutes with. On the other hand, what do we know about this? We know that the product in general of sets is the product of the, how do I say this? I know that if I take products of sets, I know what that looks like. It's the Cartesian product. And I know that if I look at the product of R modules, I get the product of R modules. On the other hand, if I look at coproducts, or sums rather, then the sum, what you get should be just the sum of the pieces, because in the category of R modules, that category is abelian. And so in R mod, sums are almost the same as products. They coincide in the case that they're finite. And sometimes they call this byproducts because mathematicians have a sense of humor and they went for a pun. So what that means then is that if I do this with sums and products, those are different limits, right? They're dual notions. But on the level of sets, the coproduct of sets is the disjoint union. Which is not the same thing as the Cartesian product, as I'm sure you're all very much aware. And so we're seeing a failure for the forgetful functor to be compatible with these particular pair of limits. Now, Kashiwara and Shapira give us a reason, or maybe if you like, an enhancement for this argument, a generalization. I'm not really sure if I think of this as a rationale for this argument, or rather as a generalization. I leave it to you guys to decide. What they do is they think about lim as a functor itself. And they think of this as a functor which eats functors and returns sets. In particular, it's a functor from the category of functors of a particular shape to set. And I'm sure there's some way to enhance this so that it happens on the level of small categories or something, and that I doesn't have to be fixed. But we don't have to worry about that for this little conversation. Let's just think of I as a fixed thing. This functor doesn't commute with even finite projective limits. And we're going to see why. And so how do we understand this? Well, what happens is we suppose it does, for the sake of a computation. Let's look at the simplest finite projective limit. That's the product. Then what we do is we know that if this forgetful functor commuted with the product, then it would follow that the following little calculation would make sense. We could have such a product like so, and this would give us this product. Of course, I and I are indexing set everywhere. But here's the catch. This guy has an operation because it's a module. Well, I'm only worrying about the additive structure, so really it's a group, but it doesn't matter. The point is, because I have a map mi cross mi to mi given by this operation, I can apply this operation and map this back to here. And the problem is that this is, in general, not given a group, right? Because we have made this is into sets, so this doesn't work in general. And so, for this reason, this calculation must not be possible. Something must have gone wrong. And so, in particular, there can't be this commuting. So, the goal of this section and of subsequent sections, really in this whole chapter, is to enable us to sort of get around this problem. We want to introduce a notion of a kind of limit. These are our filtrant limits, or really even prior to that as a filtrant category, which will be a category for which the forgetful functor from our module category will commute with limits. So maybe I'll write this down as idea. Find a notion, or rather a definition, for which the forgetful functor commutes with projective limits under these hypotheses, whatever the definition is that I'm looking for. And of course, this is going to be our notion of a filtrant category. So the point of all of this, like I said, is sort of build us towards homological algebra as much as possible. And also sort of in this chapter, as we start to encounter these ideas, I'm going to maybe borrow, should I say, from some homological algebra texts, and I'll sort of point you guys to the right stuff as we need it. But for now, we don't have to stress about that, just as a sort of heads up for the future. Okay, so let's jump in and let's start with our notion of a filtering category. So we have a definition. We have a non-empty category. This is sort of a thing that only appears like one place, I think, in the whole chapter. But nevertheless, we include it. So we have a non-empty category, and it will be called filtrant, or filtered if you prefer, if it satisfies the following two conditions. Let me scroll. There we go. Yeah, I don't know if you guys know this, but I record this by obviously handwriting on a Windows Surface, so sometimes it can be a little picky. So condition 1, for any pair of elements, there is a K and morphisms, which I'm not going to bother to name, I, J, 2K. And for any parallel morphisms, and these guys I will name, call them F and G. Let's say they go I to J. There's a morphism J to K for some K with HF equals HG. Oh, of course I didn't. Yeah, I'm stupid. That morphism is the morphism H. So what's this definition saying? Well, it's kind of like saying that there are coproducts and coequalizers. And I really need to emphasize that kinda, because we're not insisting that these morphisms in the definition satisfy any universal property. And so if you were like me, you might have wondered as a youngling, like what the point of the universal mapping property is. Like, okay, why isn't the important part about the product being that there are projection maps? Why is it that it's the unique object through which every other such object factors through? And this is sort of why. Like in general, what we're going to see is that filtrant categories are quite different than categories which in general have coproducts and coequalizers. In fact, we saw that in the chapter 2 that having coproducts and coequalizers is the same thing as being co-complete. And, there's no reason that you need to be co-complete to be filtrant. In fact, one thing that's sort of possibly enlightening is that a very frequent example of filtering categories, maybe this is like example 0, but I'm not going to write this down super precisely, is any category with a terminal object. Is filtrant. And of course, that tells you how to handle 1, and similarly for 2. Just map everything to the terminal object. There's always one morphism, and because it's terminal, there's only one morphism to it, then all of these conditions are just automatically satisfied. But just because you have a terminal object, that says nothing about being complete, or sorry, co-complete. And so this is it's a pretty substantial difference, just to sort of give maybe some insight into that. So probably one question you have off the bat is, what the heck does this have to do with what we said before about having, wow, I lost my words there. What does this have to do with having the forgetful functor be compatible with any sort of limit? And we're going to see this in the coming videos. What we're going to do in the rest of this video is just sort of enlarge our knowledge of what this definition is, and we'll sort of build towards establishing filtering categories having this nice property. So we have a lemma that starts our discussion off. And this is that a category is filtrant. We're sort of rephrasing what it means to be filtrant. If and only if, for any finite j, and any functor, phi j to I, there is an I such that the limit over all of the j's hom phi j I is not empty. Okay, and how do we prove this? Not so bad. Sort of a brief argument. So, of course, for one direction, we assume that I is filtrant, and we set j and phi as in the statement. And so, since j is finite, there is an I0 such that, or I want more things, but so maybe before I say such that, there's an I0 and also some morphisms, which I'll index by the elements of j, so we'll call them Sj, phi j to I0 for all j. And moreover, there are some morphisms kj and lambda j, and again, depending on j, such that the following composition does not depend on the first map. So what we do is I map phi j to phi j prime to I0 to k. And of course, I didn't tell you what these maps are. The maps are phi t, for some, of course, t. And then I have Sj prime and lambda j. I'm just going to write them down here. Okay, so now there's also an object I1 and a morphism which we could call Cj, which goes Kj to I1. And finally, a morphism I1 to I2, such that we have the chain I0 to Kj to I1 to I2, and none of this depends on j. And so this family of morphisms that we've such constructed, we can call these Uj. We have Uj, which goes phi j to I0 to Kj to I1 to I2 by putting all this together. This defines an element of the desired limit. So the limit is not empty. So that's one direction. For the reverse direction, you don't have to work as hard. We can just check the conditions in the definition. So maybe I won't write this down. I'll just explain it. For the first condition, what you do is you take j to be the category which I called 2 in the past, which has just 2 discrete elements. And if that is not empty, then that tells me that I have this this sort of roof definition, the sort of coproduct type object. And for the other condition, what I do is take the category j to be the category with 2 elements and a pair of parallel morphisms. And then if there's a limit, then that, or an element of the limit of these homs, then that tells me that there's this co-equalizer-esque condition. And so both are satisfied and the category is filtered. So I think this next result is going to be the last result that we're going to do in this video, just for the sake of time, because we've already been talking almost 20 minutes. What I'm going to do is explain my remark from the intro to this video, where I'm going to tell you why filtrant categories are sort of the ones that are like the p-adic numbers. What I want to do is explain to you how to calculate with filtrant categories, if you will. And we'll call this a proposition. So we have alpha from I to set, a functor. And we're going to assume that I is small, because if I want to calculate with stuff, it better be small, and filtrant, because everything is filtrant. Now I define an equivalence relation which I'll call tilde, because that's what we always do, on the disjoint union of the alpha i's by declaring x is equivalent to y if and only if there's an x that looks like an alpha. Let's try to be careful. If there's an x in alpha I and a y in alpha j, with, of course, I different from j, and a pair of morphisms, which I'll call ST, S I to k, T j to k, such that alpha of S of x is equal to alpha of t of y. And under these conditions, I know I'm really running out of room. Let me try to zoom out and squeeze it in a little bit. Under these conditions, of course, this should be an equivalence relation. And the limit over alpha is the coproduct of the alpha i's modulo this equivalence relation. Now, this is not a tremendously difficult thing to prove if you've been sort of with us the entire time. So I don't think I want to try to write out the entire proof because back when we were in chapter 2, we had this section 2.4, which I didn't do in the video series. I sort of glossed over it under the assumption that everyone was familiar with these limits. But nevertheless, this is essentially a completely straightforward consequence. What is this? Proposition 2.4.1, which was basically how to calculate with limits in set. And so if you were with that section, then you should see this immediately. And if not, then you should go back and have a look at it and sort of refresh your memory. So for those people who don't know about p-adic numbers, who didn't want to watch my very long distraction video, let's try to clarify what's going on here just a little bit. I think of my category I as like a big tree. Or, I mean, we always think about categories as like directed graphs, which sort of contain the objects, and then the limits and colimits that we want to construct. These are sort of universal objects on one end of the construction. This was the story about cones and cocones that we saw. And so the idea is that if there are paths in this graph which are sort of never forced to come back together, then by the first condition, how do I say this actually? So what's going on is that this is sort of tameness condition. When there are paths in the graph that sort of do crazy things, we can get wild classes, which sort of break our ability to use this quotient construction. How should I say this? This is a complicated thought. I need these sort of roof and coequalizer conditions to sort of tame everything out. Because what's happening is no matter how crazy my graph is, when I have two guys, everything always sort of eventually points back together. And there are always ways to sort of equalize stuff. Oh, sorry, I'm supposed to call these F and G. So the point is that these conditions sort of bring together the various maps. And of course also then the objects. And sort of tame down our category into something which is kind of tree-like. And the commutativity condition in 2.1 is sort of telling you that all these classes are sort of represented and appear in a somewhat tame way. On On the other hand, if there are no maps that are sort of playing the role of the co-equalizers, then there's not much really tying all this together in the disjoint union, and so we sort of end up with more classes than you might expect there to be. Or there, on the other hand, there could also be sort of relations between these things that can't be unified, again, sort of without this commutativity condition. And so without this, we sort of end up with this chaotic mess of relations or points, if you like, in these objects. So as a corollary to this, let S be a finite subset of lim alpha. Then there is an I such that S is contained in the image of alpha I. By the natural map. What am I doing? Alpha I to lim alpha. There we go. And there's a part 2, which is that for I and I, x, y in alpha I, with the same image in the limit, then there exists an S, I to j, such that alpha sx equals alpha sy. In alpha j. Okay, so I don't want to give the whole proof of this, again, sort of for the sake of time. I just want to sort of give you an idea for the argument. What you do is you argue by induction. If S has cardinality 1, this is basically trivial. On the other hand, if I assume that it's true for cardinality k, then what I can do is find the element realizing the statement for a given set with cardinality k. And then I can do the same thing for the additional singleton. And then to get to k plus 1, I can use the roof condition in the definition of filtrant. And then the commutativity of the diagram ensures that this element has to do the job. And the second claim, this is again very much like what's happening in the p-adics. What's happening is if these things are defining the same class, then at some point, at some actual, if you like, for p-adics, it's some finite stage, but in some actual stage in alpha j, so to speak here, then these things have to actually coincide. So if you want to sort of see how this works, then just pop open your commutative algebra text and sort of remind yourself how it works in that case, and then stare at the proof really hard, and you'll become convinced that all of this is exactly the same in this case. Okay, so I think that's a good place for us to stop. We're going to pick up next time in the next video, where we're going to talk about this business of the forgetful functors and the IPC property. Probably some of you guys are a little bit annoyed because you're like, you said all these words about filtrant categories, but you didn't tell us what it has to do with the very discussion that you motivated. Yeah, you're right, but you know, hour-long videos are hard, and I'm also learning this stuff. So it's best for the best of us, for the both of us, if I take some time and continue to make sure I get this right. So we pick this up next time in the very near future. Hopefully we get to the IPC property. Mostly what I want to do is make sure in the next video to have time to talk about forgetful functors and limits. And we're going to do a computation that sort of explains what this does. Okay, so hopefully this has been enlightening, and I will catch you guys in the next one. So until then, take care.